Hello, scholars. So this week we are learning about the ANOVA, analysis of variance. An ANOVA is a group differences test, much like a t-test. However, it can handle more than two groups or two time points. The t-test can only compare two groups or two time points, like pre-test to post-test for time or men versus women, two groups. And ANOVA could do more than two, okay? And we have different types of ANOVAs, okay? We can have a one-way ANOVA, which is what we're going to do today. It can test for differences between two or more groups. We can do a repeated measures ANOVA, which tests for differences over time points, like the dependent t-test, but it can do more than two time points. Like pre-test to post-test is a simple dependent t-test, but what if I wanted to do winter, spring, and fall? Or I wanted to do the end of each month on all 12 calendar months. That's a repeated measures ANOVA. And then we can do a mix of the two, such as, is there a difference in participation, treatment versus control, from pre-test to post-test in some score? So I've got a between groups categorical variable, treatment versus control, a within groups categorical variable of time, pre-test and post-test, and it can compare the groups every way you can think of, such as, most people would want to know, did the treatment group do the best post-test? But it can compare them every way you can think of. And ANOVA is like multiple t-tests. So a one-way ANOVA can do multiple t-tests between all of your groups, compare them every way you can think of. Okay, so it typically uses mean average scores if you're doing a parametric test. Okay, so it could answer, is there a difference in runtime between groups A, groups B, and groups C? And it would compare group A and C and group A and B and group B and C to one another. And we could find that out. Okay, so the assumptions, the data assumptions of a one-way ANOVA, this is between groups, that we have one independent variable and one dependent variable, excuse me. One dependent variable measured at the continuous level. Okay. So that means it's interval or ratio variable. We have one categorical variable with two or more groups. And then we have independence of observation. A participant cannot be in more than one group. Okay. And then we have testing assumptions for an ANOVA, like each group is approximately normally distributed, approximate normality bell curve, and homogeneity of variance, meaning the variances or the distance between scores for each group are about the same. So today we're testing the research question, is there a statistically significant difference in performance? So performance is our dependent variable, right? Between age groups, 18 to 25, 26 to 36, 36 to 47, and 47 to 60. Okay. So that's what we're testing for. Notice we have 1, 2, 3, we have 4 groups here. So is there a difference between these 4 groups? So the first thing I'm going to do is I'm going to want to run my data. So open your JASP file, and first we're going to order our normality test and our descriptives, skewness, kurtosis, histograms, everything you want. So remember, We're splitting on age. That's our categorical variable. And then we're testing performance in our case, okay? And I can order my statistics. So you're supposed to order skewness and kurtosis, and I want my normality test. Okay, so here we go. And if you look at it, here's my p-value. And remember, to understand if this normal, the null hypothesis for a normality test is that the null hypothesis states everything is normally distributed. So if the null is normal, p has to be greater than 0.05. Okay, so let's look at that. So here's my p-value of the Shapiro-Wilk on that same test. And p, well, for each group, is greater than 0.05. So in my case, the assumption of normality is met. Okay, report that in APA 7, which was covered in another video. Now, to run my one-way ANOVA, I'm going to go back to analyses, and I'm going to select ANOVA. I'm going to go to the classical menu and just click ANOVA. And my dependent variable again is performance. And my categorical fixed factors is age. I can select my descriptive statistics again. And I can order my assumption checks by clicking on assumptions over here and ordering my homogeneity by just clicking it. Okay, now let's give this a moment to catch up and let's see what we have. So remember, my null hypothesis then would be that there's not a difference in performance between age groups. So here's my ANOVA test. Here's age. Here's my F statistic, because an ANOVA is an F test. By the way, so is a homogeneity test. And then here's my p-value. My p-value is p is less than 0.001. That is significant. So I'm going to order an effect size. We'll talk about that in a moment. Now here's my assumption test. So I tested normality above already. Here's my Levene's test. Are the variances approximately equal? The null hypothesis states everything is equal. So if I reject the null, they're not equal. My p is 0.121. P is greater than 0.05. So my assumption of homogeneity is met. Okay. So I retain the null hypothesis. P is greater than 0.05. The assumption is met. So now I'm going to go back and I need to order an effect size because I found something. Now, if I didn't find anything, I don't need an effect size. In our case, we did a Cohen's D for an effect size for a t-test, but for an ANOVA, we're going to use the partial eta squared. That looks like this kind of n here squared. It says partial. So click estimates of effect sizes and click the partial eta. That's what we call this n here, partial eta, right? And now you can see, I don't need the W. Okay, you can see this partial eta was added to my ANOVA test. That's my effect size, 0.373. We will discuss what that means momentarily. Okay. Now, let's say I had violated homogeneity of variance. If my homogeneity of variance was p was less than 0.05, I can order a non-parametric test. I can order a non-parametric test with violated normality, violated homogeneity of variance, and definitely want to order it if both are violated. So my non-parametric test is the Kruskal-Wallis test. And I would move age over to the right. And if I had a significance, there's where I order the effect size. But see, here's the Kruskal-Wallis test. And P is also, it's significant, 0.001. So I would add my effect size. Again, I'll use a partial eta. Okay, a partial eta squared should be added somewhere to my test here. It's updating. And I could see the partial eta is 0.368. Now, because there's a significance, I order a post-hoc test. Lots of times when you're done with your inferential testing, you need a post-hoc test. So I'm going to go to this arrow over here for post-hoc, and I'm going to move the categorical variable over again. I'm going to leave it on standard here. I'm going to click effect size, and I'm going to use a Tukey. Now, a Tukey compares all of these groups every which way they can be compared. So this is group 18 to 25. And it does a t-test. Remember I said an ANOVA was multiple t-tests? And it gives me an effect size. Okay, here's the p-value. So I can go look over here and see which of these group comparisons were significant. Well, group 18 to 25 was significant compared to all the other groups. So there was a significance between group 18 to 25 and group 26 to 36, between 18 to 25 and 37 to 46, and 18 to 25 compared to 47 to 60. But there was not a significance between the other ways we could compare groups. You see that? No significance there. So why was group 18 to 25 significant compared to all the other groups? Well, let's look at this mean difference here, right? Here's the mean difference, right? We can see it. So 18 to 25 was 1 full point at least less than all of the other age groups in performance. So their mean average was lower than everybody else's. And you can see here's the p-value. That's how I know. I had 3 less than 0.05. Here's the effect sizes. Cohen's d, remember for a t-test, that's how big of an effect. And look, it was a huge effect for all of them, right? If you remember Cohen's cutoffs, anything over 0.8 was a big effect. That's covered in my t-test video. Okay, and then here's the t-statistic. Okay. So now we know that there was a statistically significant difference between age groups because the youngest age group performed worse than all the other age groups, period. Okay, but there wasn't a big difference between the older age groups. Now, let's talk about how I write this up. Okay, so you noticed here's my assumption check for Levine's, and I would just say the assumption was met. P was greater than 0.05 right here, or I can say P equals 0.121. All right, there's my Kruskal-Wallis test in case you need to know how to do that. Look, I color-coded for you how to write it up. Now, this is the non-parametric test. This is the one, if your assumptions were violated, you'd use. And you can see it. Look, x squared, chi-square. 3 is your degrees of freedom. Here's my Kruskal-Wallis statistic, 25.056. My p-value and my effect size, which is large. We'll cover how large in a minute. And then we can look at how to write it up if it's a regular ANOVA test. F, comma, parentheses 3, comma 60. Why is it like that? Why are there two? Well, because for a regular ANOVA test, the degrees of freedom are a fraction. Okay. So the numerator is the number of groups minus 1. We had 4 groups. 4 minus 1 is 3. So the numerator is 3 over 60. Okay. And that would be probably the same as my sample size. So the degrees of freedom in an ANOVA is a fraction. So that's why we have two numbers here. There's my F statistic right there, my p-value, and my effect size. Now, we also use Cohen's cutoffs for partial eta, but the cutoffs look different than a Cohen's D, right? So the cutoffs here, a small effect is 0.01 up to a 0.06. A 0.06 up to a 0.14 is medium, and anything over a 0.14 is large. Okay. Now let's look again at that post-hoc Tukey, right? So a Tukey is t-tests comparing each group every way they could be compared. So that's why we have a T statistic instead of an F statistic, because each of these represents a t-test. The ANOVA does it all at once, but it doesn't tell us which groups were significant. That's why we do this post-hoc comparison, okay? And then we can report all of that all at once, right? So I would add to my ANOVA results that a Tukey's Honest Significance Test, HSD, was conducted as a post-hoc analysis following a statistically significant ANOVA. The test revealed significant mean differences between the age group 18 to 25 and all other groups. The age group 18 to 25 was significantly less in performance. So I would conclude by rejecting the null hypothesis in favor of the alternative, and I would say there was a statistically significant difference in performance between age groups, with age group 18 to 25 performing significantly less than all of the other age groups. Okay, I hope this explains both how to use JASP to run your ANOVA and how to interpret it. So remember, when you write your papers, first you give your descriptives and you talk about your distribution. Then you're going to test for normality, you're going to test for homogeneity, and you are going to run your ANOVA test. And if there's a difference, you do your post-hoc and effect size. If there's not a difference, you simply fail to reject the null. Okay. If your assumptions are violated, you use the non-parametric Kruskal-Wallis test and interpret P the same way and refer to in the video how to report it in APA. Thank you very much.